Hello and welcome back to this lecture on mathematical foundations on machine learning. Namaste to everyone. We in the last class, like last 4 classes, we have looked at the idea of probability events, then we looked at independent events, then we looked at Bayes theorem and so on. And in the end of the last lecture we said that we need to gain some more insights as to how this definition of probabilities probability and things stand very concrete with strong mathematical foundation, and in that context I also introduced this idea of probability space, right, which is basically a triplet which has the sample space and then a collection of events and then a function which is going to map the set of events to a or each event in that set, whatever you call B, we give a name for that, to a real number between 0 and 1, and we call that real number between 0 and 1 for that particular event as the probability of occurrence of that event. So what we will do is in this lecture we will try to understand what this actually means. And you remember we also had this one of the axioms of the probability which said the probability of any event is always greater than or equal to 0, and we really had this question which is always lingering in mind: why should probability of an event be bounded between 0 and 1? In fact we had some explanation regarding this, but we will continue to in this lecture to concretize those ideas, right. In order to understand that, we first need to understand that there is something called as a measurable space, a measure space and a measurable space. I will not get into the extreme details of this measure theory or the idea of measurable space, much details I will not do because it is beyond the scope of this course, but I just wanted to give you certain insights about how things are happening and how is it that these axioms have been defined, and does it actually conform to something else, alright. We want to look at all that, and that will be the focus of this lecture. So in the last class, if you look at, we stopped at defining this what would you call as this omega, then b and p. We said this is going to be there, and we called this as the probability space, whatever that it meant. We really did not understand what is this probability space. We just said, look, this is the structure that is required, like how we had in vector space the idea of field, then the collection of vectors, and then there are certain operations, then we had the closure of this vector space or the set of vectors under certain operations, and then we said that if this closure is all there, then we said that look, we have a vector space, and we are going to do something similar to that here, but of course not in the I am just trying to say that there is a fundamental structure even for probability, and that is what it means here, right. So we have this omega bp which we call as the probability space, and let us get into the details. And I mean there are quite a few good books on measure theory and probability. You can look at measure theory by Professor Krishnathraya Lahiri, then you have measure theory by Terence Tao, and you have probability and measure by Phil Billingsley and so on, but these are trying to get you into the depth of your what would you call probability. It will be good if you can go through that, but for the sake of giving a little bit of clarity, I am including those ideas here. We will restrict our things to probably a discrete sample space, because continuous sample space and things will involve a lot of understanding of intervals, and then so we will not look into that. This is just to give you an idea that this is how it happens. So that is what we are going to do in this lecture, okay. So let us get it. So we defined this omega bp as a probability space and one more thing, this whatever that I am trying to do here is basically material based on the article published by Matthew Bernstein. So you can probably look for his GitHub page, and which actually gave a wonderful elementary insight to the idea of measure, the idea of measurable space, measure space, and then everything culminating in the idea of a probability space. So, I have looked at the article that he has written. It is a 3-part article, where in the first part he discusses about the basics of measure theory, the idea of measure space and measurable space, and what is a measure, and then he discusses about random variables, and then he goes on looks at expectation and expected value and things. So, what I will do is I will just restrict my discussion to just probability, because of this current week what we were doing is on probability, right. We will restrict our discussions to the idea of probability. So, what are we going to do? So, the first question is we are going to make this definition. We say that okay. So, we say that probability space is nothing but a measure space, probability space omega BP is a measure space where P of omega is equal to 1, right. Now, there seems to be, it is like you asking a student, why did you absent yourself from the class? He says, look, yeah, I absented myself from the class. So, this you do not get the reason. So, here when I say probability space, you again put another jargon and say, look, it is a measure space where the probability of whatever that omega is equal to 1. So, we had some ambiguity before, and we have landed in a different ambiguity now. So, what is this probability space, what is a measure space, and what does this all mean? So, that is what we are going to look at now. Okay. We already know this notations. We say that okay, omega is nothing but the sample space associated with a random experiment. This is the sample space we have, and we are going to make this, we are going to say that look, this B is not something new, we know what this B is. This B is basically the collection of events, of omega, and we are going to give a name for this collection of events of omega. We will come to it, we will just give this a name, and then we will see what must this collection satisfy, what properties must this collection satisfy, collection of events of omega called the sigma algebra. And what are we going to do? We are going to have the third component, which is basically this P, which we are going to say that look, this is nothing but measure for the measurable space, measure for the measurable space is given by omega and the collection of subsets of omega, and we call this P as the probability measure. We call this as the probability measure, right. So, now there are too many jargon again. We wanted to know what probability was, but then we said look, you land up in probability space, and in the probability space you associate a measure, and that measure is equal to 1. Now, we do not even know what a measure is, and then we say that look, you try to look at the collection of events of omega, which you call as the sigma algebra. I think these things are like kind of creating a lot of trouble. So, let us try to figure out what each of these things mean. So, for that what we do is we need to resort to some elementary ideas, we need to look at certain elementary ideas of measure theory. So, what does this measure theory do? Basically, it basically is the abstraction of the idea of a size, abstraction of the idea of a size or volume or whatever it is, idea of a size, I will say of size, right. So, what does this size mean? See, the point is we are trying to look at something, we keep talking jargon and we have landed in one more stuff here. What is that? Size. Now, what does that even mean? We do not know what is measure, we do not know what is size, but then we say look, it is the abstraction of the idea of size, whatever that word size means. So, let us look at what it is. So, let us look at, so what is the size? Size is nothing but a number we attribute to an object that obeys a specific property. What is the property? Suppose you have an object, let us say you have this mouse or whatever, you have this object. Now, what you do is you break it into two pieces, right. Now, what do we say? You break it into two pieces, and then if you try to take the mass of this mouse before you break the mouse, the mass of this mouse before you broke the mouse should be equal to the sum of the pieces that you have got after breaking the mouse, right. So, that is the intuitive property that we are looking at. So, what are we going to say? We are going to say that if we break, what is the property? The property is basically this: if we break the object, the sizes of the object or the sizes of the broken pieces must add up to the size of the whole, to the size of the whole. That is quite natural to ask. Say suppose I had a 1 kilogram of a cake and then I cut it into 10 pieces. If I add the mass of all these 10 pieces, it must add up to 1 kg. You will not get a surprise saying look, it is about 1.5 kg, that does not make sense, right. So, basically that is what we are looking at. So, when we say a measure, this measure the size that we talk about, the size must be such that it obeys this property. When you break a bigger object into pieces, and then what you must get is the sum of the sizes of the pieces must be equal to the size of the whole. This is a very important property. So, the question is how do we break this into pieces, how do we break a given object into pieces, and that is exactly where we get into the idea of our measure theory, right. So, the question is how do we partition it, or how do we size, or how do we break this entire object into pieces, okay. So, let us take this simple example. So, what are we going to do? We are going to look at this. So, I am using the same notation as what we have for our probability, because it will be easy to establish one on one correspondence. Typically textbooks use for the whole object they will use the notation f, and then this whatever collection of subsets it is going to use some script f and so on, but I will just use this omega so that we have in our back of mind that we are trying to work on the sample space and on the event. So, what we will do is let omega be the whole object we are considering, be the whole object we consider. So, you can take the example of this cake. right. You can take the example of the cake. So now what we do is so we ask for, okay, so given omega, we now need to describe, or we need a way to describe how omega can be broken down into pieces, can be broken into pieces. Okay. So that is exactly where we come into the idea of sigma algebra. So what we do is we will say that the idea of sigma algebra, so the sigma algebra, this is another mathematical structure that you have, sigma algebra over omega describes the notion of breaking omega into pieces, of breaking omega into pieces, right. So what are we going to do now? So we are going to define the sigma algebra. So what are we going to do? We are going to say that given a set omega and a collection of subsets of omega, we will call this, and we will put the script b, and we call this, and this is basically the collection of subsets of omega. We will do this. B is called a sigma algebra, B is called a sigma algebra if it obeys the following properties. If it obeys the following properties. What are the properties? So the first property is very interesting. We say that the empty set is an element of B, phi is basically the empty set, right. And the second property we are going to say is if A is an element of this B, then A complement also belongs to B, A complement is also an element of B, right. We will give an interpretation for all these things, like that will make it quite interesting and understandable, right. The third one, it says if A1, A2 etc. are elements of this B, then the union I is equal to 1 to n AI is also an element of B, right. This is what it means, this is what it is. So what it says is this is the property that we are looking at. If you break it into pieces, the sum of sizes of these pieces must be equal to okay, we will come to it, it is not about even size, it is something else very interesting. So what we say is if this happens, then the union of these broken pieces, or if you try to glue the broken pieces together, that also is an element of this P, that is what it means. So what is the interpretation? So first of all, what are the interpretations we have? So let us write that, interpretations. So what must be, I mean we said that, look, I have an object now, this is basically my omega object, let me take this, let me put this here, assume that I have this object omega. Now what I do is I try to break this object, and then those broken pieces are going to be the ones which are going to get into B. So I will say that okay, this is A1, this is A2, this is A3, this could be A4, you could have all these things, right. So, you have these to be the objects. Now, what are we trying to do? So, first thing we understand is, look, each element of the sigma algebra, each element of the sigma algebra each element of the sigma algebra B is basically a piece of the object that you broke, is basically it represents the piece of the object, represents a piece of the object. Number 2, a null piece, that is basically the interpretation of this. A null piece is also an object, is also considered a piece of the object. Well, as I write, I am quite sure that you will be able to get the correspondence to our idea of probability. I am quite sure we will be able to do, if not we will be doing this as a part of this lecture. So, just do not worry. So, the third one, the third point that we have here is, if we break an object A, okay, if we break off this is basically this interpretation, the interpretation for the second point, we say that if we break off a piece A from the object, the remaining piece, which is basically the A complement, the remaining piece A complement is also a valid object. The third one that we have is basically this. The third one is this, the third property which we have written there. The interpretation is this: if we glue a countable set of broken pieces together, the resulting piece is also a valid piece of the object, is also a valid piece of the object. This is interesting, because all these things were what we saw in the axioms of probability. We said that of course, notwithstanding the idea of probability, we said that if the idea of if an event, if there is an event A complement is also an event. That is the second property that we had. If A is an object part that we have, it is a broken piece of the object, whatever is remaining is also a valid piece of the object. Therefore, that is exactly why we end up saying, look, when I toss a coin, I ask for, okay, I am interested in the event of getting a head, but when that event head does not happen, that means tail has occurred, that means even that is an event. That is exactly what we are coming to. An event not happening is also another event, complement of it. That is exactly what it means here, right, brilliant. Okay, so let us go ahead. what is more interesting, see this sigma algebra whatever you have seen, it says look it must be closed under complementation, that means you put a complement will get into that bag which is called the big B or the sigma algebra B. If you take number of pieces a1 a2 a and a1 a2 a infinity, you take these broken pieces and then glue together, you get another piece, that means it is, that is also a valid object. So that what you say, it is closed under countable union. Now you might have all studied your De Morgan's law in your set theory. So the moment I say this, look A is there, A complement must get in, B is there, B complement must get in, if A and B are there, A union B must get inside the sigma algebra, that basket B. Now what happens is, because A union B gets into the big basket B, A union B the whole complement also gets into the big basket B, A union B the whole complement is nothing but A complement intersection B complement, that fellow will also get into it. So you will have the sigma algebra to be even closed under intersection. So what we are going to say is, we are going to say that sigma algebra is also closed under, is also closed under intersections differences, we will say set differences and symmetric differences. These are operations that you would have studied in class 10 12 or 10 11 about when you do the idea of set theory, symmetric differences, right. Okay, so now, well, we have defined the sigma algebra, we had a set, we had an object, we broke those objects, and when we broke those objects, the collection of all the pieces must obey certain properties. What is that? If you put one piece into the basket, rest of the remaining piece is also a valid piece of the object, we said that. You can have the entire piece without breaking it, therefore that will be a complete piece, and you will also have a empty set which does not contain anything, but that is also a valid element of this, the sigma algebra or the big B, the basket big B. And then what we said, look, if you glue all the broken pieces, not all the broken pieces, a finite number of broken pieces or a countable infinite set of broken pieces, you get another object, but that object is also from the original object only, that is what it says. So it is also a valid piece of the original object. So these are the properties. Now I have all these properties, what do I do? I am going to get into the idea of, or the notion of measure. So let us look at this. So finally what is going to be measure? So let us look at this. So what is a measure? So basically what it does, it is a function first of all, it is a function that assigns each piece of the object a size. Of the object a size, and we already know what is the property of this size and other things, that we have already we had that notion of size where it says if you add the what do you call the size of the broken pieces, sum of the size of broken pieces should be equal to the whole, the size of the whole. So that is what we had. So what we are going to do is we are going to look at we are going to make a definition here. So we are going to say that given a set omega, and a sigma algebra B on omega, the function let us say mu that maps B to R. What does this mean? the domain of the function is basically the elements of B and the range is basically the set of real numbers, basically the real line. Okay. The function B mu which maps from B to R is called a measure, if it obeys the following properties, What are the properties? We are going to look at it. Number 1, for all elements of B, for all let me say A in sigma algebra B, the measure of A is always non-negative, greater than or equal to 0. Then the second one, the measure of the empty set, is 0. The third one is nothing but countable additivity. We are going to say this is countable additivity. What are we going to say here? We are going to say that given a countably infinite sequence of sets, given a countably infinite sequence of sets, A1, A2 etc. A1, A2 etc. elements of B, elements of the sigma algebra, where we are going to say this, where AI intersection AJ, that means the you take any two sets from B, they must be disjoint. That means the broken pieces that you take two broken, there cannot be what do you call, you should say that these are individual pieces, they have nothing in common. So, AI intersection AJ is basically the empty set. Then the measure of union I is equal to 1 to infinity AI. You remember the union of AI, we said it is basically an object. I have an object, I broke those objects into A1, A2 etc. Now what I do is I glue the objects together, that is basically taking this union. So what I am saying, the measure of this union is equal to the sum of the measures of individual objects. So sum of measures of the individual objects I is equal to 1 to infinity. If all these properties hold good, these three properties hold good, we actually call this mu to be a measure, right. So what is the interpretation? Again we are looking for interpretation. This implies the measure or the size must be non-negative. This says size must be non-negative. See, the moment we say measure, you cannot have a negative measure. You can't go to an oil, you can't go to a kirana shop and then ask this guy, can you give me minus 2 kgs of sugar? It does not make sense. So the measure must be non-negative, either you do not ask anything of sugar there, or you ask something, a positive quantity or positive weight of quantity of the sugar or any object that you want. You are not going to say give me a negative 2, right, that is not going to work. And what about this? This implies the null set which has no elements, null set has size 0. So what does this mean? This actually means the following: sum of sizes of separate pieces, separate pieces of an object must equal the size of those pieces when glued together. when glued together. That is what this means, right. Okay. So, what are we going to do? So, we are going to say this, we are going to define this. So, we are going to make a definition here, we are going to say that the triple omega B mu is called a measure space where omega is a set, B is a sigma algebra on omega, and mu is a measure of omega and B. Right. Now, let us map all these things to, okay, let us first take an example of the sigma algebra and a given set. Let us take just simple one example and figure out if you are able to understand what we are talking. So, consider this omega, let us take omega to be this set 1, 2, 3, 4, and I am going to define 3 sets, namely A, B and C, where A is going to be the singleton 1, B is going to be the singleton 2 and C is going to be this pair 3, 4, right. Now, I want to get the sigma algebra defined by these guys or generated by these 3 guys. So, first of all A is there, therefore, A complement must go into the sigma algebra. So, what is A complement? A complement is 2, 3, 4. B is there, B is the set that you are considering. So, therefore, B complement must also go into the sigma algebra, which is nothing but 1, 3, 4. Then C is 3, 4. Since C is also any what you call a broken piece we are considering, the C complement must also go in there, which is nothing but 1, 2, which is nothing but 1, 2, right. Now, what are we looking for? We are looking for the union of all these sets. You have to look at, if you have A, then A union B must be there, which is already C complement, then A union B union C must be there. Therefore, the union is nothing but the union of, let us say, A, B and C. So, we have to have this. So, A union B union C, which is nothing but the entire set itself 1, 2, 3, 4, which is equal to omega, and since omega is there, omega complement which is equal to empty set must also go inside. Therefore, I am going to say the sigma algebra generated by, so sigma, okay, let me write it in the next page. So, we have this. So, the sigma algebra generated by A, B and C is B is equal to, first of all, empty set must go, then the set A is there, set B is there, then set C is there, then we have C complement which is 1, 2, then we have A complement which is 2, 3, 4, then we have B complement which is 1, 3, 4, then we have A union B union C, which is omega itself. So, this is the sigma algebra generated by A, B and C, right. You could also have another trivial sigma algebra where I take my event, I would not say event, the largest piece, the unbroken piece to be the only piece that I have. So, in that case, suppose I take A is equal to, second example, suppose I take A is equal to omega itself, then the sigma algebra B will be equal to sigma algebra B would be equal to A, which is omega, and the complement of this, which is nothing but empty set. So, that is the trivial sigma algebra that you have, right. So, you can okay, probably you can even try this out. I will give you another example. So, let us take example 3. Let me define the set omega, which is 1 2 3 4, right, and now I am going to define A, which is nothing but okay 1 2 3 4 5 and 6. Let me take that, which is basically the set of outcomes for rolling of a die experiment. So, I have A is equal to 1 3 and 5. Now, I would want you to find out, try this, find the sigma algebra generated by A, right. So, this is one interesting thing. Now, okay, fine, where are we heading to from here? This is, we saw that in the case of okay, we defined what is measure, we defined what is sigma algebra, we defined what is measure space, and where are we getting to for the probability space. So, what we are going to do is a probability space is nothing but a probability space is a measure space, space is a measure space where the measure of the entire object or the measure assigned to the entire object is 1. Assigned to the entire object is 1. That means we say this, the entire object is 1. So, we say P of omega is equal to 1. This is what we had, and if you recollect, we had a lot of we made these axioms and all those things. Now, it becomes very clear as to why, if A is an event, now you know A complement is also an event, because what is happening, our probability function that we have here, say suppose I have a probability space which is omega BP, this is the probability space, this is the probability space. Now, what happens is this probability function P will take an element, let us say E for any element E in, let us say B, right, it must be an element of this set B, and it will assign a value between 0 and 1, right. Now, by virtue of E being an element of B, E complement is also an element of B. So, what we say is the measure, when we put this measure idea, we say that measure of E plus measure of E complement must be equal to the whole, and since the measure probability measure for the whole is 1, we have the probability measure of E complement to be equal to 1 minus the probability of E. And the moment you talk about probability of E complement, we always said the measure is basically associated only with the fellows who get inside this sigma algebra, this B. The probability measure is always associated with elements of this B, not all possible subsets. In fact, that is exactly where we defined our events. The idea of events was to say that, look, event is nothing but subset of our interest. The moment you say I look for a subset of our interest, that fellow will go and sit inside this B, and the moment that subset sits in, we know that, okay, if there is a chance of it raining today, there is also a chance of it not raining today. This not raining becomes complement, and that complement will also sit here, and in that way you also see the sample space being an event, empty set being the event, and everything else follows, right. So, this is basically the background for the idea of the measure theoretic idea behind this probability assignment and probability mass or the total probability being 1 and all those things. And in fact, even the idea that probability of an event is a non-negative number between 0 and 1, it is a non-negative number and is between 0 and 1, it tells us that it also conforms with the definition of any other measure that you take. No measure is basically a negative value. So, all those that you measure are basically non-negative value, and that is how this probability measure also fits the bill. So, we will stop with this, and in the next class we will start with the next week with the idea of random variables, where even random variables take require the definition of this probability space. You will be able to understand that the moment in the random variable case I say a probability of x taking a value is equal to this number, you must be able to understand that it is going to be a map between one measure space to another measure space, and the probability of a random variable taking a value will exist provided there is a pre-image in the event space. If it is not there, then you will not be able to define probability. I hope you got this very elementary way of understanding this probability measure and stuff in this lecture. In the next lecture we will start with our idea of random variables. Namaste.